Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 12, Organic Chemistry 2. We are still in chapter 3, Reactions of Aromatic Compounds, and we will continue on talking about electrophilic aromatic substitution. Briefly, what we covered last lecture is the reaction of benzene with active electrophile leads to substitution where carbon hydrogen in benzene replaced by carbon electrophile. And the mechanism for that is the first attack on the electrophile, forming sigma complex, and sigma complex is stable via delocalization of the positive charge, what we call resonance. The second step is deprotonation and regaining aromaticity of the ring by losing the H, forming again the double bond and getting substituted benzene. The reaction works in two steps. First step is approaching E to form first transition state, which is a rate determining step. Then forming sigma complex, which is still higher in energy than the starting material since it's non-aromatic, and then losing the hydrogen to form second transition state, and then the product. So it's two steps: addition, elimination, and net for that is what we call substitution reaction. Friedel-Crafts alkylation of benzene. Friedel-Crafts alkylation of benzene. In 1877, these two scientists discovered that haloalkane reacts with benzene in the presence of Lewis acid aluminum halide to become much more powerful electrophile, R, the alkyl group. The resulting products are the alkyl benzene and hydrogen halide. So the reaction of benzene with alkyl halide in presence of aluminum halide forms alkyl benzene. But how does this activation work? We know that this is a polar bond, right, from organic chemistry and in general chemistry. But when the alkyl halide react as a Lewis base with aluminum halide, Lewis acid, to form acid-base complex, this is much more polar. So, and this carbon carries much more partially positive charge and can be recognized now by the benzene electron clouds. So it attacks on this carbon, kicking AlX4 out and forming sigma complex, which again stabilized by resonance, then elimination of proton to form alkyl benzene. Although Friedel-Crafts alkylation is effective with ethyl chloride, with the other primary alkyl halide cannot used effectively. Why? Because we can get molecular rearrangement, hydride shift, methyl shift in the primary carbocation, as we know that from organic chemistry 1. So, alkyl halide primary with aluminum chloride forming this complex. As we mentioned that this has tertiary positive, then could be rearranged hydride shift to form secondary, more stable ion pair with aluminum AlCl4-. You may find it in other books that they draw it this way first and then rearrange to form this one. Anyway, the benzene with primary alkyl halide, we get the compound, the alkyl halide, alkyl benzene, and we can get the rearranged product. It's always, you have a mixture. So you get here, you start with butyl chloride, you get butyl benzene, but you get mixture with secondary butyl benzene, and it is a major product. We would like to get this one, but we get this also. So the mixture of products is unavoidable. Okay? With secondary and tertiary alkyl halide, free carbocations are usually formed as an intermediate. So here is clearly, if we started with tertiary butyl chloride, what we call it in IUPAC to chloro to methyl propane, you get the complex dissociation to form tertiary carbocation. And then the tertiary carbocation attacked by the benzene by bond, forming sigma bond, sigma complex, and followed by deprotonation to form tertiary butyl benzene 1,1-dimethyl ethyl benzene. Intramolecular Friedel-Crafts alkylation can be used to fuse a new ring onto benzene nucleus. Starting with 4-chlorobutyl benzene, primary here, alkyl halide, okay, in the presence of aluminum chloride, carbon disulfide, nitromethane solvent mixture at 25 degrees Celsius. Provide 1, 2, 3, 4 tetrahydronaphthalene. In this particular case, we did not see any rearrangement, okay? Since first, carbon disulfide work as non-polar solvent, minimizing separation of ions for the complex to dissociate. The second reason is the 6-member ring is more stable than 5-member ring. The reactivity of haloalkane increases with the polarity of CX bond in the order of RF is faster than RCl, faster than RBr, faster than RI. Typical Lewis acids are borotrifluoride, antimony pentachloride, iron 3 chloride, aluminum chloride, and aluminum bromide. As we mentioned that alkyl fluoride is the fastest and can be catalyzed by boron trihalide. Scientists found that the boron trihalide catalyzed alkyl fluoride and benzene, the reaction of alkyl fluoride and benzene, but cannot activate alkyl chloride or alkyl bromides. Friedel-Crafts vinylation or arylation employing haloalkene or haloalenes do not work, since this carbon is sp2 and the carbocation will be energetically inaccessible, so there is no reaction. We cannot create actually by reacting vinyl chloride and aluminum chloride, we cannot create carbocation, unstable. Okay. Friedel-Crafts alkylation can be carried out with any starting material that functions as precursor to carbocation, such as alcohols and alkenes. We know that alcohol with Lewis acid-like borotrifluoride form complex, and this complex is not stable, will dissociate and give carbocation. This carbocation react with benzene under this condition to form sigma complex, followed by deprotonation to provide alkyl benzene. So, alcohols with borotrifluoride at 60 furnish alkyl benzene. Also, if we take benzene with alkene, react that with hydrogen fluoride, okay, what we got? We got cyclohexyl benzene. How that? Cyclohexene reacts with HF to form carbocation, addition of H+. This carbocation reacts with benzene to form sigma complex, followed by the protonation to give the product. Isopropyl benzene is synthesized from propene and benzene in the presence of phosphoric acid. Write the mechanism. The first step is the protonation of propene with phosphoric acid, Markovnikov, so the hydrogen will add to this carbon, forming secondary carbocation, attack on by benzene, forming sigma complex, followed by deprotonation to form isopropyl benzene. What is the limitation of Friedel-Crafts alkylation? The first limitation is a multiple alkylation are hard to avoid, since you react benzene with alkyl halide in presence of aluminum chloride, you form alkyl benzene. The presence of this group, we will come to it later, the presence of alkyl group on benzene activate the benzene, make it faster than benzene. Okay, so we will get dialkylation, trialkylation, and of course some of unreacted benzene will be seen in this reaction. Okay, Friedel-Crafts alkylation is susceptible to carbocation rearrangement. So starting with propyl N-propyl bromide, you get the primary, then you get hydride shift to get the secondary carbocation, you end up with arranged product isopropyl benzene coumarine. Another limitation, if we have on benzene substituent, we call it deactivating group, like nitro, and again we will get to this later, what's meant by activating and deactivating. If we have deactivating, you try to apply Friedel-Crafts condition, it doesn't work. Okay? So nitrobenzene cannot be alkylated under this condition, alkyl halide in the presence of aluminum chloride. Friedel-Crafts acylation of benzene. The key reactive intermediate is not a carbocation itself, but acylium carbocation. Starting with acid halide, using aluminum chloride as a catalyst, they will interact to form Lewis base, lone pair donator, aluminum chloride, lone pair acceptor. So Lewis acid base complex will be formed by these reactions. We have two possibilities: either interact with the lone pair of halogen to form polarized complex, dissociate and form acylium ion. Another possibility is the lone pair of oxygen will form a complex which is more stable than the upper one via resonance, right? But there is an equilibrium, and the equilibrium will shift to the acylium ion at the end. According to Le Chatelier's principle, we are going to consume acylium ion in the reaction. If we use acid anhydride, which is another reagent, again with Lewis acid aluminum halide, will form the complex. Of course, also with this lone pair is the other possibility. So we have here complex which will dissociate to form again acylium ion. The formed acylium ion in the media will find the benzene, so the pi electrons will attack on, forming sigma complex. A sigma complex will lose deprotonate, to lose H plus, to regain aromaticity and form a ketone. This ketone will find out aluminum chloride, will form a complex. So we have to add water at the end. When the work up of the reaction, at the end of the reaction, we add acidified water to get the free ketone. Here are some examples of this reaction: benzene with butanoyl chloride, a little bit more than 2 equivalent aluminum chloride. Then after the time of the reaction is over, we treat it with acidified water to get 1-phenylbutane 1-on. We may use anhydride, like in this case acetic anhydride or ethanoic anhydride, we call it in IUPAC, ethanoic anhydride. Again, a little bit higher than 2 equivalent aluminum chloride, then treated with acidified water to get acetophenone. How do we synthesize alkyl benzene that cannot be made by Friedel-Crafts alkylation? Well, first step is treating benzene with acid chloride and aluminum chloride. Second step, acidification, treated with aqueous acid, get the ketone, then just reduce the ketone, transfer the C double bond O to CH2. How we can do the transformation of this function group? Clemmensen reduction, treated the compound, the ketone, with HCl and amalgamated zinc amalgam, HCl. It's one step. We can transfer easy the carbonyl compound to alkane. Or we can do Wolff-Kishner reduction. Take the carbonyl compound, treat it with hydrazine, form hydrazone, then treat the hydrazone with potassium hydroxide as a base. Well, you can do it in one part, or in just two steps. You can isolate the hydrazine and work it up. Multi-step synthesis using first sodium borohydride to transfer C double bond O carbonyl to alcohol, and then transfer the alcohol with HBr to alkyl halide, the OH to HBr with HBr. Then treat the alkyl halide with lithium aluminum hydride to exchange Br by one hydrogen. Okay, that's organic chemistry 1. Let's have an example for that. Identify whether 2,2-dimethyl-propylbenzene, new bentyl benzene in common name, can be made using direct Friedel-Crafts alkylation. According to this connection approach, we take this compound that comes from, you cut here, so it's benzene and 1-chloro-2,2-dimethylpropane, and this is the carbocation we need that comes from this when it reacts with aluminum chloride. Well, if that's the case, this compound 1-chloro-2,2-dimethylpropane with aluminum chloride will form this complex, might dissociate, or we can just look at it as dissociated. It's primary carbocation. We can get methyl shift to form tertiary carbocation, which is more stable. So we are expecting this to occur. According that this one is the formed tertiary carbocation, react with benzene, and the product will be 1,1-dimethylpropylbenzene. It's not 2,2-dimethylpropylbenzene, but we need this compound. How we can do it? Okay, if we can start instead of the CH2 with C double bond O, which has no rearrangement, okay, then again cut in here. So we need this acid chloride with benzene in presence of Lewis acid. Okay, take this compound, aluminum chloride, form the complex, dissociate that, forming a acylium ion, this one, no rearrangement, that will react with benzene to form this ketone, that is methyl tertiary butyl phenyl ketone, common name. Then treat that with zinc amalgam HCl, heat up, you get the compound. You just use this to CH2. Recall from lecture 28, Organic Chemistry 1, that the carbonyl, upon reduction with sodium borohydride, this will be HOH. Treating this alcohol with HBr, then you transfer the OH to Br. Reacting the alkyl halide with lithium aluminum hydride, substitution, you will substitute the Br by H and you get CH2. So we have three methods to transfer C double bond O to CH2: Clemmensen reduction, Wolff-Kishner reduction, and this multi-step procedure. First transfer it to alcohol, then to alkyl halide, then to alkene. The formyl chloride is unstable. See, acetyl chloride, okay, we can have it, but formal chloride is highly unstable. Accordingly, the Friedel-Crafts and the Kraft did not able to synthesize benzaldehyde using their method until Gattermann-Koch came up in 1897 with a method. They took carbon monoxide under pressure, treated with HCl and Lewis acid, aluminum chloride, copper chloride mixture, and they were able to get inside, prepare in situ the formal chloride. So carbon monoxide with HCl, you add the H to the carbon, forming the acylium ion. Chloride will attack on to form formyl chloride. You have aluminum chloride in the medium, Lewis acid. So you form the complex, which dissociate again, once again, to the acylium ion. This acylium ion will be attacked by the biclouds of benzene ring to form sigma complex, followed by deprotonation to form benzaldehyde. This is the Gattermann-Koch method. See you in next lecture. Bye.